Hello and welcome to this comprehensive lecture series on rail vehicle dynamics. We are delighted to be your companion as we explore the fascinating world of railroad engineering. Whether you're a student, a practicing engineer, or simply passionate about trains and transportation, these lectures are designed to be accessible, engaging, and grounded in real-world applications. Railways are a vital part of modern infrastructure, and today, they are evolving faster than ever. This series is especially timely because India is on the cusp of a transformative era in rail transport. Our first lecture will focus on high-speed trains. India's first high-speed rail corridor is set to become operational very soon, marking a milestone in the country's transportation history. This corridor will not only reduce travel times drastically, but also elevate the standards of safety, comfort, and efficiency. We will explore the technologies and engineering principles that make these trains possible and how the global high-speed rail systems can be compared. Thank you for joining the channel on this journey. Together, we will uncover the principles and innovations that drive the railways of today and tomorrow. Let's get started with our first lecture on high-speed trains. The images used in the video have been taken from various sources. Same has been acknowledged along with the image. In the last of the video, you will be knowing the sources on which this video is based. You may refer to them for further readings and information. Hello everyone, and welcome to our comprehensive lecture on high-speed rail systems. Before we dive into the fascinating world of high-speed trains, let me walk you through the structure of today's presentation. Our session is organized into 7 key parts that will take us from fundamental concepts to detailed comparative analysis. In the introduction, we'll set the stage by establishing the platform for this learning journey. We'll discuss why high-speed rail matters in our modern transportation landscape and highlight the relevance and importance of understanding these sophisticated systems. The second part will focus on the common characteristics that define high-speed rail systems around the world. We'll explore what makes a rail system high-speed and the fundamental features that distinguish these systems from conventional rail networks. In the third part, we'll examine the technological advantages of HSR systems. This will include their efficiency, environmental benefits, and the various ways they transform connectivity between urban centers. The fourth part will address the technical challenges involved in implementing HSR systems. Here we'll cover the complex engineering, financial, and logistical hurdles that must be overcome when developing these advanced transportation networks. From the fifth part onwards, we'll narrow our focus to the rolling stock aspect, specifically the HSR train designs themselves. We'll look at the components, systems, and engineering principles that make these trains technological marvels. In the fifth part, we will discuss the basics of HSR train designs. In the sixth part, we'll take a global tour of HSR trains, examining the distinctive approaches developed in Japan, France, Germany, and China, the pioneering nations that have defined high-speed rail technology. Finally, in the seventh and perhaps most illuminating section, we'll conduct a comparative analysis of these major high-speed train designs. We'll evaluate their strengths, unique features, and performance characteristics to understand what distinguishes each approach. By the end of this presentation, you'll have a comprehensive understanding of high-speed rail technology, its implementation challenges, and the various design philosophies that shape these remarkable transportation systems. In this video, we will cover the first 4 topics, that is, introduction, common characteristics of HSR, technological advantages, and the challenges. The last 3 topics will be explained in the next video. We will start the introduction with the need to understand the relevance of topic. As we all know, Vande Bharat trains, the semi-high-speed trains, are the talk of our country today. It is tested at the maximum permissible speed of 183 km per hour, and its maximum operating speed is 160 km per hour. This second image is of the 1000 class Shinkansen taken in 1963. 1000 class Shinkansen is one of the 2 prototypes Japanese high-speed trains built for high-speed testing ahead of the opening of the Tokaido Shinkansen in 1964. It was tested at a speed of 256 km per hour, and its maximum operating speed was 200 km per hour. The third image is a French TGV train, which made the world record for highest speed of 574 km per hour for wheels on rail in 2007. The maximum operating speed of TGVs in France is 320 km per hour. This slide clearly suggests that as Indians we have a lot to do in the direction of achieving high speeds on rails. The research has divided the evolution of high-speed trains into 3 leaps. First leap from conventional train services is known as WHSR transportation system, that is wheel high-speed rail mainly running on the railway track, also called the conventional high-speed rail. The operating speed of WHSR is 200 to 400 km per hour. It has frictional resistance and air resistance. The second leap consists of MHSR, that is the magnetic suspension type HSR, which is mainly suspended on rails to run. It is also called a superconducting high-speed rail. The operating speed of MHSR is 400 to 1000 km per hour. MHSR has air resistance but no frictional resistance. Only commercially working line of MHSR is in China at Shanghai Airport. At present, only Germany, Japan, China, and South Korea continue to conduct research on magnetic levitation systems. The third leap is SSR system, that is a MHSR transportation system suspended in a vacuum pipeline, also called a vacuum high-speed rail. The operating speed of SSR is more than 1200 km per hour, without friction resistance and air resistance. HSR has been in service since 1964. HSR provides a high-speed, high-capacity, low pollution and high energy efficiency modern transportation tool. Many countries are developing their HSR system. New technologies are being developed. Integrated intermodal transportation planning is being done by countries. As of today, high-speed rail is working in 20 countries and is under development in 7 more countries. Some examples: in Japan Shinkansen, in France TGV, in Germany ICE, in Italy ETR, in Belgium Thalys, in Sweden X1000, in Spain AVE, in UK Eurostar, in Taiwan THSR 700T, in China CRH, in Russia Subsun. India is on the way to build its first HSR. This is the list of 10 major countries where HSR is running. At present, China is having 40,414 kilometers of HSR in operation. This is about 70% of the total HSR kilometers in the world. The second column shows the year of opening the service of HSR in that country. The third column shows the maximum operating speed presently. The current maximum commercial operating speed is 320 km per hour in France for TGV, Germany for ICE3, and Japan for Hayabusa and Komchi Shinkansen. The Chinese high-speed railway that opened between Beijing and Tianjin, having about 115 kilometers of track, in August 2008 in conjunction with the Beijing Olympics, initially started at the world's fastest commercial operating speed of 350 km per hour, and the high-speed railway between Wuhan and Guangzhou, consisting of 968 kilometers, that opened in December 2009, also started at 350 km per hour. However, the 23rd July 2011 collision and derailment at Wenzhou, Zhejiang province, caused speeds to be lowered to about 310 km per hour. However, the speed record for iron wheel on rail high-speed trains is 574.8 km per hour, set by TGV high-speed train developed by Alstom based on the test train that set this world speed record, was dubbed by the ETR 575. This is a graph taken from a UIC report showing the evolution of maximum test speed and maximum operating speeds on rails. A spike in maximum speed can be noticed near 1990s. This is due to the rapid surge in the fields of power electronics, smaller and faster switches in the form of IGBTs, and in AC traction. As we have already discussed, the maximum test speed has been limited to 574.8 km per hour, and maximum operating speed has been limited to 350 km per hour. Now we will look into the definition of a high-speed rail. Yes, there is no unique definition for high-speed rail. UIC has defined it as the rail operating at more than or equal to 250 km per hour. European Union has defined it into types. For upgraded infrastructure, if the rail operates at more than or equal to 200 km per hour, it is called high-speed rail. And for new infrastructure, if the rail operates at more than or equal to 250 km per hour, it is called high-speed rail. In Japan, the official definition is a main line on which a train is able to run at over 200 km per hour along almost all the route. USA has defined HSR into forms. HSR Express, which is frequent, express service between major population centers 200 to 600 miles apart, having few intermediate stops, dedicated line, and top speed of 240 km per hour. HSR Regional, which is relatively frequent, stations 100 to 500 miles apart. Some intermediate stops, top speed 180 to 240 km per hour, with some dedicated, some shared track. Having defined the HSR, now we will look at the various components of high-speed rail. High-speed rail represents far more than simply trains moving at elevated speeds. It constitutes a sophisticated, integrated technological ecosystem where every component embodies cutting-edge innovation. This is what truly sets HSR apart from conventional rail transportation. To fully appreciate the marvel of high-speed rail, we must examine it as a cohesive whole. The exceptional performance of these systems emerges from the seamless integration of multiple advanced subsystems working in perfect harmony. No single element can deliver the HSR experience in isolation. A world-class HSR system integrates these critical components: infrastructure, meticulously engineered tracks, bridges, tunnels, and stations designed to exacting specifications that accommodate extreme speeds while ensuring passenger comfort and safety. Rolling stock, precision-engineered train sets featuring advanced composite materials, optimized aerodynamics, and state-of-the-art propulsion systems that push the boundaries of rail technology. Signaling and control systems, sophisticated electronic networks that maintain safe train separation and enable split-second decision-making at velocities where human reaction time would be insufficient. Power supply and distribution systems, high-capacity electrical networks delivering consistent, uninterrupted power to trains operating at the edge of performance envelopes. Maintenance systems, specialized diagnostic equipment, and preventative protocols that ensure flawless operation and extend system lifespan. Station emplacement and operation rules. Comprehensive regulatory frameworks governing everything from track access to emergency procedures. Financing innovative funding approaches that address the substantial capital requirements of these transformative infrastructure investments. Marketing strategic passenger attraction initiatives that maximize utilization and optimize revenue streams. Management expert organizational leadership combining technical excellence with operational efficiency. As we explore HSR implementations across Japan, France, Germany, and China, we will identify the universal principles that unite all successful systems. However, equally fascinating are the distinctive approaches each nation has developed in response to their unique geographical challenges, technological capabilities, and cultural priorities. These variations offer invaluable insights for countries developing new HSR systems, demonstrating that while certain fundamentals remain constant, the path to high-speed excellence accommodates thoughtful adaptation to local conditions. In the second part of the lecture, we will be discussing the common characteristics of HSR systems implemented in various countries. While high-speed rail systems worldwide exhibit distinctive national characteristics, They're unified by mainly 8 fundamental engineering principles that form the technological foundation of all successful HSR implementations. The cornerstone requirement is purpose-built infrastructure. Unlike conventional rail upgrades, true HSR demands either entirely new alignments or comprehensively reconstructed corridors engineered specifically for sustained high-speed operation. This infrastructure features dedicated lines exclusively for high-speed services, eliminating the operational complexities and safety risks associated with mixed traffic. Complete grade separation represents another non-negotiable characteristic. Every potential intersection with roads, pedestrian paths, or other transport infrastructure must be eliminated through tunnels, viaducts, or overpasses. At operational speeds exceeding 250 km per hour, even minor level crossings would present catastrophic safety hazards and fundamentally undermine the system's reliability. The dynamics of high-speed operation necessitate exceptionally generous curve geometry. While conventional railways might function with curve radii of 1000 meters, HSR requires radii exceeding 4000 meters. This isn't merely for passenger comfort, though that's certainly important, but because the physics of high-speed operation generates centrifugal forces that would otherwise compromise wheel-rail contact dynamics and accelerate infrastructure degradation. Similarly, increased track spacing, minimum 4.2 meters compared to conventional rail's typical 3.5 meters, addresses the sophisticated aerodynamic challenges unique to high-speed operation. When trains pass at combined relative speeds approaching 300 km per hour, they generate pressure waves powerful enough to potentially destabilize trains or damage their exterior components without this expanded clearance. The absolute prohibition of level crossings follows directly from both safety imperatives and the operational requirement for uninterrupted high-speed running. The emergency stopping distance for an HSR train set can exceed 2 kilometers, rendering traditional grade crossings fundamentally incompatible with the system's basic physics. Contemporary HSR development has converged on standard gauge 1435 mm rail technology. This standardization facilitates international interoperability, enables cross-border services in regions like Europe, and allows manufacturers to develop technologies with broader market application. The track itself universally features continuous welded rail, eliminating the joint gaps of conventional track. Beyond providing the renowned smooth ride quality of HSR, this continuous rail profile is essential for maintaining precise wheel-rail dynamics, reducing maintenance requirements, and minimizing the transmission of vibration to the trains and passengers. There is a need for specialized lightweight, streamlined rolling stock having light and sophisticated bogies with superior suspension. We will discuss this in details in the second video of this series. Finally, advanced in-cab signaling systems replace conventional trackside signals, which become entirely unusable beyond 200 km per hour. These sophisticated digital systems transmit comprehensive movement authorities, speed restrictions, and track condition data directly to the train's onboard computers. This enables real-time speed supervision and automatic train protection, critical safety systems that prevent human error from resulting in catastrophic outcomes at such extreme velocities. These 8 defining characteristics represent the technical consensus of the global high-speed rail community. Yet within this framework, fascinating variations emerge across different national systems. Individual HSRs are unique. Japan's Shinkansen is an example of dedicated service with separate high-speed tracks that exclusively serve high-speed trains. There are 3 models for mixed services. Mixed high-speed trains are exemplified by France's TGV. This model includes both dedicated, high-speed tracks that serve only high-speed trains and upgraded, conventional tracks that serve both high-speed and conventional trains. Mixed conventional are exemplified by Spain's AVE, which has dedicated, high-speed, standard gauge tracks that serve both high-speed and conventional trains equipped with a gauge-changing system, and conventional, non-standard gauge tracks that serve only conventional trains. Then there is a model for fully mixed services exemplified by Germany's ICE Intercity Express. There most of the tracks are compatible with all high-speed, conventional passenger and freight trains. Most of the high-speed rail systems are built on standard gauge technology. The closest to Indian Railways broad gauge, 1676 mm, is the conventional line having a gauge of 1520 mm between Moscow and St. Petersburg in Russia, on which Subson high-speed trains are run at a maximum commercial speed of 250 km per hour. Tilting trains have not been included in this comparison. Now we will be discussing the technological advantages of implementing an HSR system. In the third part of the lecture, we will discuss the advantages of the HSR systems. Building on our understanding of HSR's engineering foundations, let's examine the 6 key operational advantages that distinguish high-speed rail from other transportation modes. First, HSR delivers an unmatched combination of speed and capacity. Operating at 250 to 350 km per hour, these systems transform 3 to 4 hours journeys into 60 to 90-minute connections. With headways as short as 4 minutes, HSR can run 12 trains hourly in each direction, moving up to 15,000 passengers per hour, equivalent to approximately 24 jumbo jets or a 10-lane highway at peak efficiency. No other transport mode achieves this speed-to-capacity ratio. The safety record of HSR systems is extraordinary. Advanced train control systems using redundant digital technologies maintain precise tracking of every train set, automatically enforcing safe separation distances. HSR demonstrates remarkable operational resilience across diverse weather conditions. Unlike air travel with its weather-related cancellations and highways with their precipitation-induced slowdowns, HSR maintains consistent service through rain, snow, moderate fog, and typical seasonal conditions. The energy efficiency of HSR creates both environmental and cost benefits. HSR spatial efficiency is particularly valuable in land-constrained environments. A dual-track HSR line with capacity exceeding 24,000 passengers hourly requires only a 25-meter right-of-way, compared to 75+ meters for a highway with equivalent theoretical capacity. This land conservation advantage is crucial when routing through urban areas, agricultural regions, or environmentally sensitive zones. Modern HSR systems achieve dramatically reduced environmental impact. Noise barriers, vibration dampening, and aerodynamic designs minimize sound footprints, while electric propulsion eliminates local air pollution. Finally, the superior passenger experience of HSR includes generous seating dimensions, typically 20% larger than economy air travel, minimal ambient noise under 65 decibels, workspace amenities, and the freedom to move throughout the train. Combined with city center stations and minimal boarding procedures, these features consistently earn higher satisfaction ratings than competing transport modes. These operational advantages explain why HSR has become the backbone of intercity mobility in countries with mature systems and why ridership typically exceeds forecasts on new corridors, representing substantial return on the capital investment required for these sophisticated transportation networks. As per the data given in an UIC report of 2008, HSR has smaller land use, both direct and indirect, as compared to the road transport. In this graph, on y-axis there is door-to-door time, and on x-axis there is the distance in kilometers. It is evident that the competitive distance of HSR is 400 to 800 kilometers. For this range, HSR is advantageous over the conventional trains as well as the air journey. Now we will be discussing about the challenges in implementing an HSR system. The main technical challenge is to reduce the aerodynamic drag of the train or the air resistance. This is the formula used for evaluating the total running resistance for the Shinkansen Zero Series trains. D is the total resistance including mechanical resistance in units of kgf. V is the speed of the train in kilometers per hour, W is the total weight of the train in tons, and L is its length in meters. The text in brown color represent the air resistance in the equation. Much of the air resistance comes from the flow of air underneath the body and around the bogie units, whose rough surfaces and sharp corners produce a great deal of turbulence. The second main technical challenge is the requirement of high tractive or propulsion power, and that too with minimum rather optimized weight of the train and its equipment. Energy required is proportional to the square of the speed, and the power required is proportional to the cube of the speed. So as speed increases, the requirement of power increases to the third power. This small table gives some representative data for the Japanese N700 Shinkansen. The main features are the high power requirement, that is 17,000 kilowatt, more power per passenger ratio 12.8, and less weight per passenger ratio 0.54. One more feature to be noted is the smaller weight per power ration of the traction motors used, that is 1.29, which is due to the lightweight 394 kilograms and high power rating 305 kW of the traction motors used. These are some more technical challenges in implementing an HSR system. First, let's consider tunnels. High-speed trains often need long tunnels to keep routes straight and level. But tunneling isn't easy. Engineers face unpredictable ground conditions like soft soil or hard rock, which can cause collapses or water leaks. Plus, the pressure and vibrations from fast trains put extra stress on tunnel structures, so strong design and constant monitoring are essential. Next, there's the issue of braking distance. As trains go faster, the distance needed to stop safely increases dramatically. This means signaling systems and safety protocols must be carefully designed to handle these longer stopping distances and prevent accidents. Reliable signaling itself is another challenge. As the typical land-side signaling becomes practically dysfunctional at speeds beyond 200 km per hour, high-speed rail uses fail-safe signaling and train control systems that automatically stop trains if something goes wrong, along with backup power and remote monitoring. Another problem is lateral instability. Even on straight tracks, high speeds and heavy loads can cause lateral instability in the trains. Also, higher speeds increase vertical loads on the track. This puts more pressure on rails and sleepers, accelerating wear and reducing stability, which again calls for better materials and maintenance. The list of challenges continues. The challenges include significant noise pollution affecting surrounding environments, difficulties in maintaining stable current collection at high speeds, and the increased severity of damage in case of accidents. Additionally, passenger comfort is reduced due to vibrations and motion, navigation over switches and crossings is complex, and stringent track geometry requirements demand precision and stability. This concludes the first video on high-speed rail. In the second video of this series, we will be discussing the high-speed train pioneer designs and the salient features of each pioneer design. Thank you for your patience and time. Please like the video and subscribe the channel if you want more content like this. Thanks again and goodbye for now.